all you cool cats and kittens. This is Victoria Carlson, and today we'll be working on problem 8.74 from our Mechanics Materials textbook. So let's give it a go. Alright, so this problem asks for us to figure out the maximum shearing stress and the maximum principal stresses for the given beam across point H. So I did already, to save us some time, draw out point H right here, and I added in the forces which were acting on it in all of the directions. We are given an XYZ axis right here, and the forces acting on it are these guys. So in the Y direction, we have a negative 0.5 kilonewton force. We also have a negative 3.0 kilonewton force in the X direction, and a 2.5 kilonewton force in the Z direction. So for starters, I'm going to go ahead and solve for our maximum shearing stress. And in order to do so, I'm going to use our Moore's circle radius. I'm not going to actually draw out the circle though, because there is a handy dandy equation we can use to figure out the radius of the Moore's circle and thus give us the maximum shearing stress. So here's that equation. Radius is our normal stress in the X direction minus our normal stress in the Y direction over 2 squared. And we're going to add our tau xy squared, which is our shearing stress. And we're going to put all of that under a square root. So we don't know any of these yet, so we're going to go ahead and solve for them. I'm going to start by solving for our tau xy. So, in knowing that tau xy is a narrow rectangular beam, we are given an equation, which is in the textbook. 3 over 2 V over A. So our V is our vertical shear stress. So in order to determine which our vertical shear stress is, we're going to look at our axes. And so we are going to be using our x-axis, and that's going to be our neutral axis. So we're going to look at the force which is perpendicular to it. That's going to be our vertical shear. So that is going to be our z direction, which is going to be our 2.5 kilonewton force. So that's that guy, so 3 over 2. Times our vertical shear, which is our 2.5 kilonewtons, times our area, and our area is going to be our base times our height, which we are given in the initial problem statement. This is a 20 millimeter by 40 millimeter rectangle, so we're going to do 20 millimeters by 40 millimeters, and we are going to go ahead and actually convert that guy. That's 800 millimeters, right? But we're going to go ahead and convert that guy to meters, because that's just what you got to do. So that's going to be times 10 to the 6 to bring it over, so 800 times 10 to the 6, and that's going to be meters squared. So in order to get our tau xy, we're going to plug all of that in, including that area that we just solved for. So that is 3 over 2 times 2.5 kilonewtons over our 800 times 10 to the negative 6. Plug that into my handy dandy calculator. Turn on, okay. 3 over 2 times 2.5 over 800 times 10 to the negative 6. Close those parentheses out. And it gives us 4687.5, which I believe is in gigapascals. So we're going to want to go ahead and translate that over to megapascals. So we're going to move it over 1, 2, 3 times. That gives us 4.6875 megapascals. Oh, you can't see that barely. There you go. Cool. All right. So that went ahead and solved for our tau xy. So we still do want to solve for our normal stress in our x direction and our normal stress in the y direction before we get the radius. So I'm going to start the x direction. So in the x direction right there, that's going to equal, we want our force over our area. It's going to be subtracted by our bending moment. So our bending moment is going to be in the, okay, so we're looking at the stress in the x direction. So our bending moment is going to be the moment in the axis which is perpendicular to such, which is still the z-axis. So that's going to be our moment in the z-axis. And we're going to multiply that by the vertical distance from the neutral axis, which if you looked at our drawing, which I don't have up yet, but it's posted online, you can look and see that the vertical distance, so the entire, right, vertical distance is going to be 20 millimeters. We want to cut that in half because the axis cuts right through it. So it's going to be 10 millimeters. I'm going to write that right here, 10 millimeters. We will convert that to meters later. No worries. And then that's going to be divided by our moment of inertia. So I'm just going to write the I right there right now. First thing to figure out, because we know our force, right? That's going to be, we're looking at the x direction. Our force is going to be the negative 3 kilonewtons. Our area is our base times height, which we solved right here. So next up, I'm just going to solve for our moment in the z direction. So our moment in the z direction, we're going to look at the force perpendicular to that, which is going to be our 0.5, our negative 0.5 kilonewton force. Negative 0.5 kilonewtons. And at what distance is it acting? It's acting, it looks like it's 150 millimeters away from it. Because it's up against, 150 millimeters away. We do want to convert that to meters right now, just to save us the pain later. So let's go ahead, that's 0.15 meters. So that means our moment about the z-axis, this is my calculator, negative 0.5 times 0.15 gives us a negative 0.075, and that's going to be kilonewtons, kilonewton meters. Okay, cool. So next up, before we solve our normal force in the x direction, is going to be our I, our moment of inertia. So since we are looking at a narrow rectangular beam, that's 1/12 base times height cubed. You do have to be careful to not mix up the base and the height for this one. Did that a few times, so we'll make sure we don't do it this time. That is 1/12. Our base is 40 millimeters. We're going to go ahead and move that over 0.04 meters. And our height is a 0.02 meters, and this is the one that we cube. Plug that in the calculator. 1/12 times 0.04 times 0.02 to the third power gives us a teeny tiny number. So let's see. Yeah, okay. Gives us, would be 2.7, had to move it over 8 times 10 to the negative 8, and that's going to be meters to the 4th power. It's going to be our moment of inertia. Alright, so we have all of the variables to this equation, so we can go ahead and solve for our stress, our normal stress, about x. So that's going to be equal to our force, which I said before, I believe, is our negative 3.0 kilonewtons, over our area, which we're going to use that lovely 800 times 10 to the negative 6 meters squared, minus the moment about our z-axis, so negative 0.075 kilonewton meters, times our 10 millimeters, we're going to do 0.01 meters. Divide that all by our moment of inertia, which we just figured out. It's our 2.7 times 10 to the negative 8, 10 to the negative 8 meters to the 4. Now, that's a big one to plug into the calculator. I'm going to do it in small parts because sometimes my calculator is not so awesome. So plugging it in into all small parts, we end up, let me show you, negative 3 divided by 800 times 10 to the negative 6. That's a negative 3750 minus this guy right here, negative 0.075 times 0.01, and we're going to divide that by the 2.7 times 10 to the negative 8. Gives us a fancy negative 27 7, 7, 7. Lots of 7. 7, 7, 7. Very lucky. All right. Make that a plus because algebra, we're going to get negative 3, 7, 5, 0 plus 2, 7, 7. 1, 2, 3, 4, 7, 7. This is going to give us 2, 4, 0, 2, 7. This is going to be in kilopascals. Yeah. And we're going to want to convert it to megapascals because that's just what engineers like to work with. So we're going to move it over 1, 2, 3 decimals. So we're going to call that 24. I'm going to call it, 24.0 megapascals. Awesome. So that gives us our normal stress in the x direction. Next up, we do want to look at our normal stress in the y direction. If we were to write out the equation for that, be force over area, and we would include our moment. This would be about the x-axis, since we're looking in the y direction, we want to look in the direction perpendicular to it. But I'm going to go ahead and tell you that since we are working on the neutral axis at this point, there is no actual moment. There's no bending moment, so this whole thing actually goes to 0. It goes away. So that actually makes our solving process a little bit easier. Because now our radius of the Mohr circle is just going to be the normal stress in the x direction over 2, since that up here in the y direction goes away, goes to 0. Just makes it a little easier to write the equation out. Square that plus our tau xy squared. And we cannot forget that square root. So if I were to go ahead and write all this out, plug it in, I'll write it down here. It's going to be our 24.0 MPa. Make it easy on us, over 2 squared plus our tau xy. Solved up here is our 4.6875 MPa. Square that guy too, can't forget that, and square root them. We're going to go ahead and plug that into our calculator. 24 divided by 2 squared plus 4.6875 squared, and hold on, dang it, retry that. That we knew that was okay. 144 plus 4.6875 squared, and then click the right one, square root that answer. Looks like we got something about 12.88. I'm going to go ahead and call that 12.9. And we are still looking at megapascals. So that right there, that 12.9 megapascals, that was our radius to our Mohr circle, right? Which we solved up here, which is also going to equal our maximum shearing stress. So we can go ahead and call that the solution to one part. Yeah, there we go. Highlight that guy. We did that part. Awesome. The next part that we just want to solve is going to be our principal stresses, which is our maximum and minimum. I'm going to rip this guy off right here, set him aside for reference. For our maximum and minimum principal stresses, it's really just going to be, it's going to be this. All right, it's going to be our maximum equals our normal stress, which we figured out in the x direction, over 2 plus r. Remember, our y direction doesn't particularly matter anymore just because it all is going to sum up to 0. And our minimum is the same thing, right? Normal stress in the x direction over 2, but now it's going to be minus r. So pretty simple stuff. We're just going to go ahead and plug and chug all the numbers that we had before. So for our maximum principal, I'm going to write it out so we don't get confused. Principal equals that lovely number 24.0, nice and even, easy peas, that's MPa, over 2 plus the radius of our Mohr circle, which we determined before, to be, where'd it go, 12.9, 12.9 MPa. MPa makes it easy peas, plug that guy in. Got 24.9. Is our max principal max principal stress. Highlight that guy because that's our answer. And for our minimum, that's going to equal, yeah, well, we already wrote that out. Yeah. Normal stress in the x2 minus r radius. So 24.0 MPa divided by 2, now minus 12.9. 12, let's just call it 12 minus 12.9. We're going to have to do that math. All right, negative 0.9 MPa. And there it is. That's how we solve question 8.74 from the textbook. Hope you enjoyed. Cheers.